Hey, good morning, everyone. Thank you for joining us. My name is Gabe-Ever, my partner, and we are the facial recognition with biometric access control team. And our team consists of my partner, Mendoza, who is in charge of the software, Senior Project Director, Dr. Welch, and our project advisor, Dr. Raj, myself, who was in charge of the hardware, mechanical, and electrical. So our project objective would be to facilitate personnel entry without a badge or key. And why are we doing this? Because there's a high probability of losing your key or badge, or they end up in the wrong hands. So how are we gonna do this? We're gonna use AI to train a facial recognition system with a biometric fingerprint scanner to identify authorized users and keep non-authorized users out. So how did this project get started? Last year we had a team do this project with different specs. They used ResNet, which required an excessive number of pictures, approximately 800 pictures per user. They also used MATLAB Online, which required constant internet service. As you guys know, MATLAB also requires a license, and over time it gets expensive. It also requires a 64-bit processor along with 4 gigabytes of RAM. They did use a Raspberry Pi 4, a web camera, and a 3D printed locking mechanism, which is easily breakable. So this year we're gonna make some improvements. We made some improvements. We used Python, which is free and easily accessible. We used the Raspberry Pi 400-4, and we made sure that our system gets computed within the Pi without the need of internet service. We also use a 1080p web camera, a simple fingerprint scanner, and a deadbolt locking mechanism with metal gear servo motor. So this is the overview of our system. We first go to phase 1, where we have our data gathering. We collect facial images and fingerprint images. We combine those two, and then we'll transfer the facial images to a data set. From the data set, we will move to phase 2, our training phase, in which we train the facial images with the algorithms that we use. Once we get done with the training, we'll move to phase 3, our recognition, in which we use Python and our algorithm to do this. So how did we do this? We had a user go up to a door in which we collect 2 inputs, a facial input and a fingerprint input. If both inputs are within the authorized database, we will send a signal to a servo motor unlocking the door. If one of those inputs is not in the authorized database, we will deny access. Or if both inputs are in the authorized database, but they're not attributes from the same user, we will still deny access. So the following is our Gantt chart. We started back in August, and we've been consistent with our schedule. Currently we are on phase 6, our presentation phase. So the following is the locking mechanism that we analyzed. We looked at solenoid mechanism. Some pros would be it's fast and it's easy installation. Cons would be it needs constant power, and over time it may heat up and fail. We also looked at gear mechanism. The pros would be it's secured, high efficient, and the cons would be the installation and the design. We looked at the lever mechanism, which is a pretty simple installation, but the lever may come off or jam up. So this is what we came up with. We fabricated a servo motor box with the dimensions as displayed, and a twist knot box. We attached the twist knot box to the servo motor, and then we attached the servo motor to the servo motor box. As you guys can see the following picture, it's mounted behind the twist knob, and once it receives the signal, it will unlock the door. You can also see the torque calculation that we had to make to determine what servo motor to buy. And we can see these fingerprint scanner attached to the door and a Raspberry Pi. So how does our fingerprint scanner work? We first get an image, it converts into a matrix, pixels, and then it gets transferred to strings going across in digits of 1 and 0. The summation of each string is called a payload, and the summation of all the strings will give us the calculation percentage of comparison. This takes place after placing your finger on the scanner, and it compares the current fingerprint versus the fingerprint that's saved from the database. Once it verifies the confidence of the fingerprint, it will either give access or deny access.
As for the algorithms that we have chosen to use, the first one being the Viola-Jones algorithm. The reason for this algorithm was because the Viola Jones algorithm was made to detect the face. Its primary feature was to detect the face, and in this, there's also 4 features of this algorithm. The first one being the hard features, where a 24 by 24 window glides across an image. The image are converted to grayscale, which is values of 0 being the blackest pixel to 255 being the whitest. Within these windows, there are a collection of data to see if a hard feature exists. And what a hard feature basically is an edge, and an edge is a color difference between the pixels. As we can see here to the right, we can see the whitest pixel and then the black pixel. Within those two rectangles, there will be a perfect edge. And the way to find the value of where this hard feature is within an image, you would have to do a sum of the white rectangle and subtract by the black rectangle's summed up value in order to find like where the hard feature would be in an image. To facilitate this, the second part of the algorithm would be the interval image, which is used for the hard features to make the process faster. Each pixel must be added with all pixels that are on the top and to the left of said pixel. As we can see here, kind of the example, we wanted to find the pixel, the sum of this pixel here. We would have to add the pixel top and everything to the left of it, and we find the sum of 20. But what if a hard feature is in the middle of an image? To facilitate finding this hard feature, we would have to add the bottom right pixel by the outside top left pixel and subtract by the outside left pixel, and also subtract the top outside pixel to find the sum. The third part of this algorithm would be the ADA boost training. In every 24 by 24 window, there's about 160,000 features. The goal is to eliminate the redundant features. This is done by training each classifier with different subregions of the images. The classifiers that performed well take the highest importance, as we can see here from this image. The first weak classifier basically has the strongest weight, and the way to find the strongest classifier is by adding a bunch of weak classifiers, as we can see. The fourth and final part of this algorithm would be the cascading classifier. To make the process even faster, we would have a 24 by 24 window glide across an image, and if the strongest classifier is not detected within this sub window, then the sub window is going to be dropped, and then a new one will continue its course. And if the first classifier is found, the second one, the sub window will try to then find the second one. And if it cannot be found, then it will be dropped, and the process will continue on. And in order for a face to actually be detected, all the strongest classifiers should be found within the image. This would be the hog algorithm, the second algorithm that we use on this project. As before, the image will be converted into grayscale, and then the image is formatted into 128 by 64 pixels. The magnitude and angles of orientation gradient are calculated using a Solver unit filter, which is 3 by 3 pixels. And then the image is then separated in a grid fashion into 4 blocks, which is 16 by 16. And to the right, we have one of those blocks, which is 8 by 8, as we can see. The block is then strewn across at a desired stride to create desired overlap. This block number 2, actually moved at 2 pixels. Then a histogram is created by each block that is quantified by each stride given, which is placed into the cells containing 9 pins each. So within the first block, we see a 2 by 2 block, and hog 1 cell 1, that would be its histogram, and so on. Then it'll be normalized, and the output is a hog descriptor, which is used for the linear SVM classifier. So on this video, this is the first implementation of our project, which is a security test, where me and him were both allowed users, and I used my face and he used his fingerprint in order to try to gain access. But because those two attributes do not match to the same person, access is going to be denied, and also the project will keep on looping over and over. There's also no way of getting stuck within a process because once the fingerprint doesn't detect, it gives you 2 tries, and if it doesn't detect, then it just loops back to the video, to the window with the camera. this is the full test, as we can see here. And to the top left, we can see the terminal. My partner walks up to the camera, his face is detected. Then we can see the log turn right now, if they turn, after he pressed his fingerprint into the scanner. Then once he walks into the room, it locks in once more, and we have implemented a button for whenever he would like to leave the room, or a person would like to leave the room. This little pause, because typically a person wouldn't leave the room after they walk, and then he would press the button. There's a little time delay, and as we can see, the lock should unlock now, and then it locks back up. And as we can see, it has looped back to the camera window. As for the test that we ran, this is the confusion matrix for it, and we ran a total of 100 tests. 5 people, we trained 20 people in our model, and a total of 25 people were used. Within those 20 people that were trained, 5 people were given access, and the other 5 that were not trained were people that we used in order to try to break into our system. And we achieved false positive of 47, false positive of 7, false negative of 4, and a true negative of 42. We then achieved an accuracy of 89%, error rate of 11%, precision of about 87%, and a recall of 92%. And basically what the precision is if the model predicted somebody to be there, this is the percentage that we received. The recall being if a person was actually there, how many times did the model get this person right?
So some acknowledgements that we would like to make. First, Dr. Welch, who was our senior project director. He was always available for us whenever we had questions and would give us advices to make this project successful. Next would be Dr. Raj. Thankfully, he had an AI class that he provided and other classes during the 4 years that we've been here. We used every material that we learned, and that helped us make this project successful as well. And a big thank you to Mr. Thomas and Mr. Motes from the engineering lab, who were very helpful once it came time to fabricate. Without them, we couldn't have done it, so they also made sure that our safety was first. Very thankful for them. And finally, but not least, the students of CPU who helped us get their facial images and fingerprint images. Without them, this couldn't have been done either. So very thankful to everybody, and thank you to all of you for joining us.
Does anybody have any questions? Yes.
Can you defeat these systems with something as simple as a photograph or a mask?
Oh, so the Viola Jones algorithm, its main feature is that the face has to be it cannot be tilted, and it must be straight. And yes, a photograph would be able to, but then after you need to put your fingerprint on there, you won't be able to beat the fingerprint, so it'll just loop back onto the camera.
All right, how about a real high quality photograph of your fingerprint?
I don't think so, because the fingerprint needs so your fingerprint has ridges, and a photograph won't be able to have the ridges whenever you place the finger on the fingerprint scanner. Yes.
The biometric that you use two, right? Fingerprint as well, as a facial. Number one, why did you go with 2 versus 1?
Because so last year they only used the facial image, and it turned out that it could be beat by a picture, and so we needed to implement something very unique to a person so that our project wouldn't be able to be beaten.
Then why didn't you just use the fingerprint?
We could have, but we wanted to improve last year's project, so we decided to just add the fingerprint with it, so we have a 2-way identification system.
And the sample that you had were 10, the total were 10, right? The number of images and fingerprints that you had in your database, how many were there total?
So for a total of facial images, we're 200 for each person.
200.
Yes, and then for the fingerprint, we use 5, just in case, because there's human error whenever putting in the fingerprint. So we try to get get all angles possible.
Thank you.
Any other questions?
What was the toughest part of this project? Yeah.
So the toughest part, there were many tough parts. First one being downloading all the libraries needed to make this project run, and also we had to work with people's schedule because everybody's busy, and we needed to basically work with them as well, and also getting both features to work with each other was the tough part.
So what if you've got a gash in your thumb or things like that? How would you go about that?
You can probably, I mean, that's a unique situation, right? So you can probably have somebody else, like a manager or something, give you access in that case. Or if needed, you can have another fingerprint input into the database.
Yes.
If you're going to commercialize these things, with 89% correction rate, then it's not going to have any customers right there. How would you improve that to get it to at least maybe 98, 99%?
We would have to add even more people onto the training database, so that there's no lower error rate.
Okay, that has been 5 minutes for questions.